This question is a fairly tricky sequence of questions, and not the smallest part of the trick is understanding what malic acid's formula means. Now, hopefully after we've done organic chemistry, this will be a little bit more obvious, but there are two important parts of the malic acid, or I think I call it maleic acid somewhere else, which is a mistake. But malic acid has a hydrogen here and a hydrogen here that are acidic. So every time you get this COOH, that's a carboxylic acid group, and that's this. And the carboxylic acid groups have a hydrogen ion that can be easily donated. So I'm going to shorten this up just for simplicity's sake. I'm going to call all of this junk in here R. And so what I'm going to get is HOOCR COOH. And this is not uncommon to see. So if we went back to our data booklet and we looked at oxalic acid has a similar kind of formula. Where are you? Oxalic acid is up here, sorry. And you can see that it's got a hydrogen here and a hydrogen here that are acidic. So those are diprotic acids, and when it loses or donates one of its hydrogens, it becomes amphiprotic. And that amphiprotic species can be found here as well. So it's acting as an acid or a base. So back to our assignment. We have this diprotic acid is going to be donating one of its hydrogens. When it loses one of the hydrogens, it becomes an extremely weak acid. And so to calculate the pH, we only need to worry about one of the hydrogens reacting. And so what we're going to do is we're going to check our assumption. So we're going to take the concentration of the acid divided by the Ka, and if you do that, it's going to give you a number that's greater than 1,000. It's going to be 1,025. So we can calculate the hydroniums using the square root of the Ka times the concentration of the acid, and if you plug those numbers in, you get 0.0124899 So then the pH is going to be the negative log of the concentration of hydroniums, so the negative log of this number, and we end up coming out with 1.90. Now, a common mistake is losing the sig digs. Here, this number had 2 sig digs. This number has 2 sig digs. This number also has 2 sig digs because for pH and pOH, we start counting significant digits after the decimal. Most people had a pretty good idea on that question, and so I'm pleased about that. I would point out that this calculation worked to get the pH and the hydroniums, because the hydroniums is the Ka times the concentration of the acid. If this had been a Kb that we were using, and this had been the basic base, then we would be calculating hydroxide ion concentration using a similar formula. So I just mentioned that because that sometimes comes up and people think you can switch back and forth, and you can't. So this says the reaction of malic acid and sodium hydrogen carbonate. So malic acid we were saying is HOOC, and then I'm going to just shorten it to say RCOOH. We also have sodium hydrogen carbonate, so that's got sodium ions, hydrogen carbonate ions, and that's in water. So water is an acid or a base, and hydrogen carbonate is also an acid or base. It's amphiprotic, but this is only an acid. So we're going to go back to our data booklet, and the hydrogen malate, or the malic acid, has a Ka of 3.9 times 10 to the negative 4. So if I'm looking, 1.4 times 10 to the negative 4, 1.5, 1.8, and then 5.6. Malic acid would fit here on the acid table. And I didn't like that. Sorry about that. So We've got the malic acid is there, water is here, water is also down here. We get hydrogen carbonate in its acidic form is down here, and it's very weakly acidic. And then we get hydrogen carbonate here. So what we're going to get is the acid reacting with hydrogen carbonate, and we'll just put that in here. So what we're going to get is we're going to get the HOOCrCOOH plus HCO3 negative, because we're going to take the hydrogen carbonate in its basic form. It's got the negative charge. And one of the hydrogens is donated from our acid, so we're going to have OOCrCOOH, and this has got a negative charge, and H2CO3. And so the acid was donated from here, and it goes to here. This was my acid, this is my base, and then we get the conjugate base of our acid, and then the conjugate acid of our base. And because the strongest acid was above the strongest base, this reaction is going to be more than 50% forward reaction. So it favors the products. Now, in this reaction, it says sketch a pH curve of what the titration of malic acid with sodium hydroxide is. So sodium hydroxide is in the burette, and we're starting at a pH that's going to be low. Often these curves have like a nice little curved bit. This is the area where you've got the hydroniums that were from reacting. The malic acid is just in water, and there's some hydroniums. Then we get the malic acid, and it's reacting with the sodium hydroxides. And then we get a sort of a sudden increase in pH, and then we get it evened out, and then we get another sudden change in pH, and then we get it flattened out again. So this area is a buffer, and that's going to be the malic acid and hydrogen malate. Here will be a buffer, and that's going to be hydrogen malate and malate ion. And then up here, this is not a buffer. That's not a buffer, but this is. This isn't a buffer because mostly what we've got is strong base left. So down here, we're going to have that HOOCrCOOH and OOCrCOOH. That's what's going to be in the mix in that buffer. In here, we're going to get let me clean that up. We're going to have that negative OOCrCOOH, and then the diprotic base. But up here, we're going to just have that negative RCOO negative and hydroxide. And so that part is not a buffer, but this is and this is. We're going to have an equivalence point that's here, an equivalence point here, and this equivalence point should be greater than 7 because we had a weak acid and a strong base. Hopefully that helps make sense out of this sequence of questions.